Hello! In the last video we looked at focus stacking. Now let's have a look at correcting vignetting and geometric distortions. There is another type of lens correction that's usually done, and that's correcting transverse chromatic aberration. But I won't cover that in this video, mostly because it's not an issue with my lens at the aperture at which I'm using it. But we may have a look at it in the future. Okay, so all lenses have some defects. And if we want to get very accurate pictures, then we should try to correct them. Pretty much all photo editing software has the option to correct lens defects. And if you're using an open source software like Darktable or RawTherapee, then you're probably using the correction profiles from the lensfun database, which is freely available online. And in this video, we'll go through creating our own corrections for this Viltrox 23mm f1.4 lens. We'll try to evaluate how well the corrections work, and we'll compare our corrections to those that are already in the lensfun database for this lens. And we'll see that making your own corrections can be worth it. So before we start, I want to be a bit more specific. The lensfun database uses certain mathematical models to describe the corrections, and models are always a simplification of the real world. A good model should capture the major behavior of a system, but still be relatively simple. And we'll do some tests to see how well some of the models that are used to describe vignetting and distortion perform. Another interesting point is that real lenses vary. So a correction that's very good for one lens may not be as good for another lens of the same model. Okay, let's get started. To create a correction profile for lensfun, we have to set up an XML file, which is saved under .local share lensfun. It can have any name, it just has to end in .xml. Then we add these two tags, so the library can recognize it. Now we want to add a lens, and first we need to make sure that lensfun is able to identify it. So we add these tags, and we get their values by looking at the EXIF data of an image. For example, you can use the program EXIF tool or EXIF2 to obtain the lens model and make. For the mount, it's probably best to look at the existing lensfun database to find the exact name of your camera's mount. The crop factor is the ratio of the diagonal of a 35mm sensor to the diagonal of your sensor. So a 35mm sensor has a diagonal of 44.27mm, and the XT2 that I'm using for the calibration has a diagonal of 28.29mm. So the crop factor is about 1.53. Okay, let's save the file, and ideally Darktable, RawTherapee and other programs should now be able to automatically find our profile when we try to apply lens corrections. I say ideally because there are some special cases where it doesn't work, and the lens that I'm using here is one of those special cases. There seems to be an issue with the slash in this specific naming convention. For example, if I replace the slash by a space, a dot, a bracket, or any other punctuation mark, the profile is found, just not with the slash. Just to be clear, in general, slashes, for example when describing the aperture, are not a problem. It's just in this specific, unusual naming convention that Viltrox has chosen where it doesn't seem to work. There is a potential workaround that allows you to effectively overwrite the name of the lens, but unfortunately that doesn't work with my Fujifilm camera. I'll put a link into the video description where you can get more information if that happens to you and if you're on a different camera system. Of course, we can still use the profile, we just have to select it manually. We'll also add one more tag, which is called calibration, which will contain our calibrations. So let's start with correcting vignetting. Vignetting means that the image gets darker as you move from the center of the image towards the edges and corners. We've already talked a bit about why that happens in the video about the do-it-yourself spectroscope, so I won't cover that here. Instead, we'll focus on how to correct it. The general idea of this correction is to take a photo of a scene that is of perfectly uniform brightness, So from every point in view of the camera, the same amount of light reaches the sensor. And then we check if the image has the same brightness everywhere. And if not, then we measure how much darker the image gets towards the edges and corners. And inverting that gives us our correction, which should lead to an image of the same brightness everywhere. I'm going to go into quite a bit of detail here. If you don't care about that, if you don't care about the details or about how it works, and you just want step-by-step instructions on how to do the calibration, then you can find a link to a post that describes it very well in the video description. Okay, in the last video about focus stacking, we used JPEGs because it's just easier. But now when we look at correcting vignetting, we can't use JPEGs. We have to deal with RAW files instead. And to understand why, let's take some time to talk about how RAW files are created and edited. And we'll see why we need to use a linear space for our correction. So, loosely speaking, when we take a picture, light goes through the lens and it falls onto our sensor. There it excites some electrons, so they move around. And if twice as much light comes in, then roughly twice as many electrons will be moving around. These moving electrons represent a current, and that current is then converted into a voltage, and the voltage is measured. So if twice as much light comes in, then we'll have roughly twice as high a voltage. This voltage measurement is an analog measurement, and to use it in our digital camera, it has to be converted with an analog to digital converter. The output of these converters is limited to a certain range of values. For example, my XT2 has a 14-bit converter, which means that the voltage measurement will be one of 2 to the power 14 values. So it will be between 0 and 16,383. If twice as much light comes in, then the value from the converter will be roughly twice as large. So I've repeatedly mentioned that twice as much light means that we get an output that's twice as large. And that's a characteristic of a linear space. So as a kind of parallel, this is a linear function and that's a nonlinear function. And in a nonlinear function, twice as much input generally does not result in an output that's twice as large, but in a different value. But the values that we get in our RAW file are roughly linear with respect to the incoming light. I keep saying roughly, and that's due to various reasons, but one of them is because even if no light comes in, the camera will measure some voltage. So even without light, the output of the analog to digital converter will not be zero. For example, on my XT2, it's usually around 1020, which is about 6% of the maximum value, so it's not negligible. This minimum level or minimum value is called the black level. Everything at or below that level is considered to be black, meaning no light came in. So the first step when developing a RAW file is usually to account for the black level by deducting it from the measured values. And the values that we get after the deduction are very close to being linear in the amount of light. Actually, at that point, the values are usually rescaled, so they are between 0 and 1. So the rest of the image processing pipeline doesn't need to know about the maximum value of the analog to digital converter of your specific camera. Okay, so now we've got values that are linear in the amount of light. And this would be a good place to apply our vignetting correction. So let me show you why I keep talking about this linear space. Let's assume we've got a very small sensor with just 2 pixels. And we took a picture of a scene that had an even brightness everywhere. And let's assume that on the image, the left pixel has a value of 0.5 and the right pixel has a value of 1. They should have the same value, the same brightness, but they don't. So there is vignetting. And we can correct that vignetting by multiplying the left pixel by 2 and the right pixel by 1. So 2, 1 is our vignetting correction. What happens if we change the pixel values before applying the correction? Let's first multiply them by 5, so we get 2.5 and 5. If we apply our vignetting correction 2, 1, then we get 5 and 5. So they have the same brightness. Our vignetting correction worked. Now let's add 5 instead. So we get 5.5 and 6. If we apply the correction now, then we get 11 and 12. We didn't get the same brightness, even though we should. So our vignetting correction didn't work. And that's an illustration of some of the properties of a linear space. We can multiply by a scalar, a number, but we can't add to it or do any other more complicated non-linear operation. And as you edit your picture, you will probably do an operation that is non-linear. So for our vignetting correction to work, we have to apply it before any of those non-linear operations. If we know exactly how the JPEG is created, then we could potentially reverse all the non-linear operations, apply the vignetting correction, and then redo all the non-linear operations. But if you just get the JPEG that comes out of your camera, then you generally don't know exactly how it was created. And at least on the X-T2, there is more non-linearity involved than just the JPEG's transfer function. And that's why we can't use JPEGs to reliably compute and apply vignetting corrections. Let's try it anyway. Here's a bright JPEG on the left and a darker JPEG on the right. Now we compute the correction based on the bright JPEG. And if we apply it to the bright JPEG, then the resulting image is perfectly uniform. However, if we apply it to the dark JPEG, then it's not. And that happens even if you account for the transfer function that transforms the JPEG between linear and non-linear color spaces. Now, of course, there are complex ways to estimate vignetting corrections for JPEGs, accounting for image brightness and other factors, but that's not what we're going to do here. We're going to use raw files instead. So, I've said that right after rescaling the image would be a good place to apply the vignetting correction. But if you look at the source code of some of the open source photo editing software, then you'll find that the vignetting correction is usually applied after white balancing and after demosaicing. So is that a problem? Let's look at white balancing. I don't want to talk too much about it here, but in short, what we call white is not a fixed proportion of wavelengths. Rather, what we see as white depends on the situation. Our eyes adapt. So in one environment, we will see one spectrum of light as white, and in another environment, we will see a different spectrum as white. And to replicate that in our images, we have to adjust the relative proportions of red, green, and blue in our pixels. And what that means in practice is that the red photo sides of the image are multiplied by one value, and the blue photo sides are multiplied by another value. And those values are chosen such that when the light that's currently considered to be white shines on the sensor, then the red, green, and blue components should all give the same value. So for white balancing, we multiply pixels by number. And as we've just seen before, we can multiply our raw image by some value without messing up our vignetting correction. So applying the white balancing step before the vignetting correction is not a problem. We'll skip the demosaicing process for today because it's too much to talk about here. But in short, there's a color filter array on top of our sensor, so we only get one color at each photo site. But for a photo, we need all three colors at each site, and we get those with the demosaicing process. I've actually implemented two demosaicing methods once. One was a simple linear interpolation, and the other was the variable gradients method. And if you remember correctly, then they shouldn't be affected or affect the vignetting correction either, which would make sense, right? We're just interpolating. We're not actually changing the value of any pixels. Okay, I think we've talked enough about theory. Let's take some pictures. First of all, the amount of vignetting depends heavily on the aperture. It's usually stronger for large apertures and weaker for small apertures. For example, this is an image at f1.4 where vignetting is relatively heavy. And this is one at f11 where it's barely noticeable. So for this demonstration, I'm going to use f1.4 so the effect of the correction is most visible. If you do this for general photography, then you probably want to do the correction for multiple different apertures. And if you then want to correct a photo which was taken at an aperture for which you don't have a mapping, then you would interpolate between the existing mappings. For this demonstration, I'm only going to create one mapping. Okay, so we need to take a picture of a scene which has the same brightness everywhere. And that's actually not so easy to achieve. We can't really take a photo of a light source like a lamp or the sun because that usually won't be large enough to fill out the entire image. We also can't shine light on a white piece of paper and then take an image of that piece of paper because it's virtually impossible to light the piece of paper very evenly. So the best way that I've found is what's described on the website I mentioned earlier, to which I put a link in the video description. So we're going to use a semi-transparent piece of acrylic which diffuses light, and we'll put it in front of the lens. These acrylic sheets exist in different levels of transparency, which are indicated by the letters WH and a number. For example, 3 mm thick WH02 lets through about 44% of the incoming light. Okay, so even though the acrylic is very good at diffusing light, ideally we want the light that falls onto the acrylic to also be relatively even. So we don't want an image of, for example, the sun, because that may have a bright spot in the center where the sun is and a darker image around it. I've tried this both indoors in a room that's lit quite evenly by number of spots, but none of the spots is directly in view of the lens. And I've tried it outdoors on a very overcast day. Both settings seem to work fine. Before you take the pictures, it's probably a good idea to clean your sensor. And your sensor and your lens, and both inside and outside, like in the front and in the back. If you don't clean them, then you may end up with spots on the image, which could affect the mapping. Then we put on the acrylic. We set the ISO to the minimum value, and I'm also setting the white balance, although that's not strictly necessary. The auto white balancing would probably do a decent job, or we could find the appropriate white balance on the computer later. Next, make sure that the brightness of your image is appropriate. Ideally, we want the image to be as bright as possible without clipping. So why as bright as possible? I think the main reason is that there are naturally variations in the amount of light that hits your sensor. And if your image is dark and you only capture little light, then those variations can have a larger impact than when you collect a lot of light. Then you have to decide on the focus position you want to use. And we saw in the last video that focus breathing has an impact on the field of view of your image. So it can, at least in principle, also affect vignetting. So how big is the impact of the focus position? It will depend on your lens. Let me show you the difference for the lens that I'm using here. This is the correction when the image was taken at the minimum focusing distance, and this is at infinity. And there is a difference of about 5% at this ring around the center, and in the very edges, the difference is about 8%. So that is quite a bit. If we compare the correction at about 2 meters to that at infinity, then there's pretty much no difference. Only the very tips of the corners have non-negligible differences. So for general photography, taking one measurement at the focus position infinity is probably enough. If you want to take close-up pictures, like in macro photography, then it may make sense to take additional measurements at closer focus positions. To my knowledge, lensfun does support multiple focus distances. So you can do multiple corrections and add them to the lensfun profile. Okay, now we can finally take a picture. I actually took multiple pictures where I moved the acrylic a little between the pictures, and then I averaged the resulting corrections. And that should reduce any noise that's in the image and that's caused if there is some structure in the acrylic. So to compute the correction, you've got a few options. The first and probably simplest is to use the script that's provided in the post I've linked to. And that whole process gives you an output that you can add to the lensfun database, and you're done. But we're going to do this step by step because we want to see how it works. So we take the raw photo, we rescale it and account for the black level, and we apply the white balance. Now we want to find our correction. So we want to know by how much we have to multiply each pixel to get an image of even brightness. So we find the maximum value over the entire image, and for each photo site we divide that maximum by the value of the photo site, which gives us this correction. I'm not actually using the maximum but the 99.9th percentile, because that makes it a bit more resistant to noise. Okay, so now we've got a correction, and if you took multiple photos, then you can do this for each of them and average the results to remove some of the noise. So as long as you've properly cleaned your sensor and lens, this should be a very accurate correction. But if you save this in its current form, uncompressed, it requires about 200 megabytes of disk space. And if we do this for many apertures and focus distances, and for many lenses, then we would quickly require a lot of space. So usually the correction is approximated by using a model. For example, this is the Pablo D'Angelo model, which is often used in the lensfun database. It assumes that the brightness only varies with the distance from the image center. So the corrected brightness of a pixel is equal to 1 divided by this polynomial of the radius. So let's try to fit this model to the correction we saw just now. And we do that by just a simple optimization. We just look for the parameters K1, K2 and K3, which result in the best fit of the model to our measured data. Here's what we get. The overall fit is quite good, but we do get some differences along the edges. So, a big advantage of using such a model is that we only need to save 3 numbers instead of an entire image. And saving 3 numbers, K1, K2 and K3, takes virtually no disk space. And another advantage is that small noise in our image, as is for example caused by small dust particles, won't show up in the correction. They may have a tiny impact on fitting the model, but once the model is fit, the correction is smooth. The disadvantage of using such a model is of course that we lose some accuracy. So let's add the correction to a lensfun profile. And we can do that by adding this line. One more thing about this. The optimization we did to find K1, K2 and K3 assumed that the image center is at the central coordinate of the image. But if our lens is a little bit offset from the sensor, which can happen due to the way they are mounted or if your camera has image stabilization, then the optical center of the lens may not be at the central coordinate of your image. So there may be an offset. I've also searched for the parameters K1, K2 and K3 while simultaneously optimizing for the image center. But for vignetting, the difference was negligible. But that may not be the case for correcting distortions. Okay, so why should you do this calibration yourself when for most lenses there are already correction profiles available? Well, first of all, if you have a new lens, then there may not yet be a profile available. But more importantly, there are usually variations in different lenses of the same type. So two Viltrox 23mm f1.4 lenses may behave slightly differently, which means that the correction that is suitable for the lens that was used in the calibration may not be as accurate for your lens. So let's compare the correction for this Viltrox lens that's already in the lensfun database to the one that we've just created here. You can tell by looking at the coefficients that they are very similar, as they should be, but they're not the same. And if we plot them, then we see that there is a bit of a difference. The correction we've just created is a fair bit more accurate for the lens that I'm using than the correction in the lensfun database. So if you are using the publicly available profiles and you're not perfectly happy with the result, then it may be worth doing the calibration yourself. So if you've been following this channel for a bit, then you know that I'm building a machine to automate 3D reconstructions. And in my machine, I'm only using aperture f5.6, and I'm always taking pictures at relatively close focus distances. So I'm only using one correction. and I'm not actually using the model but the full correction to make sure that the result is as accurate as possible. That was all I wanted to say about vignetting. If you feel that there's more to say, then do let us know in the comments. But now let's move on to removing lens distortions. And as I mentioned earlier, I'm not talking about correcting transverse chromatic aberrations, but only geometric distortions that affect pixels as a whole. In the last video about focus stacking, I showed this picture, and I said that these lines, which are actually straight on the piece of paper, are not straight on the image. So our objective is to adjust the image such that lines that are straight in real life are also straight on the image. I should say that this is a property of rectilinear lenses. If you use a lens with a different projection profile, for example a fisheye lens, then this property doesn't hold. But I'm assuming that we are using a rectilinear lens. So the idea behind this correction is that we take pictures of a scene that contains straight lines, and then we identify those lines on our pictures and we check if they are actually straight. And then we'll try to find out how we have to move the pixels on our image such that these lines actually end up being straight. So first, we need to take pictures of straight lines. I've seen a few suggestions online on how to take those pictures. In the post that I've linked to, they suggest to use the facade of certain modern steel and glass buildings because they tend to be very straight. And I think that's a very good idea. I've seen another post where they put a piece of string between two sticks. I think that may be a bit less accurate because unless you make the string very tight, it will sag a little due to gravity. And so our reference line won't actually be perfectly straight. Since for my machine I'm mostly interested in close-up photography, I'll just use a piece of gridded paper. The lines on that piece of paper are very straight, so it's a good reference to use. But we need to make sure that the paper doesn't lift up and that it's not wavy like here, because that would induce some additional unwanted distortion, which would make our measurements less accurate. And you can try to tape or glue it onto something straight, but I think it's very difficult to actually get a perfectly flat piece of paper that way. The best way that I could think of is to put the piece of paper between two sheets of glass and to squeeze them together. So this is the setup that I'm using. The lines really are perfectly straight here. Of course, the glass can reflect light, so you have to make sure that you close the shutters of your windows and that you use appropriate lighting. So my pictures look like this. Distortions usually depend heavily on the focal length. So if your lens suffers from non-negligible focus breathing, which changes the effective focal length, then you may have to do multiple measurements at different focus positions. And if, for example, you usually take pictures where you focus on something far away, then it wouldn't be appropriate to use my gridded paper approach for your calibration. In that case, you'd probably want to look for a building with very straight lines. On the other hand, if you're into macro photography or product photography, then my approach will be appropriate. In this demonstration, I'm using JPEGs again, just because it's easier. If you use the in-camera JPEGs rather than those that you've developed from RAW files, then it's probably worth thinking about the in-camera corrections, because they may also apply some distortion correction. It's probably best to turn the in-camera corrections off for the calibration. And then you should be able to use the same distortion correction for both JPEGs and for RAW files. Okay, so we've got our photos. Now we need to identify points that should lie on a line. And in a little bit, I'll talk about 3 ways of doing that. But for a moment, let's assume that we already know those points, and let's think about how we would use them to correct the image. And just like before with vignetting, we're going to use a model. There are different models. This is the model that's used by Huggin, and it can also be used in the lensfun database. As before, the model assumes that the correction only depends on the distance of a pixel from the center of the image, which again is a simplification. We will check the accuracy of this model later. So if we use this model, then our objective is to find the coefficients A, B, and C. So now I'll show you one way of using Huggin to find these parameters. This is a rather slow way of doing it, but it illustrates the idea quite well. So let's open Huggin and add an image. Then we go to control points, and we're going to use this interface to define straight lines. So on the left, we click on a point that's on a line. And on the right, we click on another point that should be on the same straight line. And on the bottom, where it says Mode, we select Add New Line. And then we select another pair of points that lie on the same line. And you can see here that Huggin added these new points to the correct line. And now we do this repeatedly until we've got a decent number of points. Now we want to add another line. So we click on 2 points on the new line, and under Mode we select Add New Line. And we do the same thing as before. It's probably a good idea to have at least one line along the edges of the image and at least one line going through the center. Once we've got a few lines with a few points on them, we can move on to the optimization. So under Photos, Optimize, Geometric, we select Custom Parameters. Under Stitcher, we select the projection to be rectilinear, and under Optimizer, we set the variables that we want to optimize. In our case, that's A, B, and C. The D value that's written here does not refer to the same D value we saw earlier in the polynomial. Here, D and E refer to the offset of the image center from the central coordinate of the image. You could also optimize other options, but these are for different purposes. I'll put a link to a document that explains them into the video description. Now we can press Optimize, or Optimize Now, and after a short while, Huggin will tell us the parameter values that it found. They should be relatively small, well below 1. Okay, now we can use these parameters to apply the correction to images. For example, Huggin comes with a program called Fuller, which you can use for that purpose. The syntax is shown here. Don't be confused by the option - green. By default, this correction is applied to all color channels. To get the exact values of A, B, and C, we can save the Huggin project and look at the PTO file. I'd also set the option Don't Rescale, because otherwise the magnification of the image changes, which I don't want here. Okay. To add these corrections to the lensfun profile, we just add this line. And after we save it, we should have those corrections available in Darktable and other software. If we look at the corrected image, then we see that the result is very good. I've put these red lines on top of the image, which go from one endpoint of the line to the other. And if we zoom in, then we see that the correction is quite good. The lines are quite straight. They are not perfect, but still very good. In Huggin, in addition to the distortion parameters, we can also optimize the offset of the image center, in case our lens isn't perfectly aligned with the sensor. So if we do that, then we get these parameters here. And that gives us this result, which seems almost perfect, at least at the lines that we're looking at here. So the model seems to do a very good job at approximating distortion, at least for this lens. To use the offset in Fuller, we just have to add the option - offset. Using an offset in our lensfun profile is not as straightforward. In the distortion calibration line, there's no option to add an offset. However, we can add an offset to the entire lens, and we do that by adding this line to the profile. You do have to make sure that you use the correct scaling for the offset coordinates. They are scaled such that of course, that offset is then also applied to the other corrections. So that is a bit inconvenient. When I computed the optimal vignetting parameters with this offset, the result was a bit worse. Not much, but a little bit more than I would like. What you can do as a workaround is to create two separate profiles, one for vignetting without the offset and one for distortion with the offset. And then, for example, in Darktable, you do two lens corrections. The first one with vignetting, the second one only with distortion. It is more work. You have to decide if it's worth it. Now let's apply the correction that's already available for this lens in the lensfun database. And at first glance, the coefficients seem very similar, which you would expect, but the result is not very good. It's really no better than not using any correction at all. And I think that's probably due to two main reasons. One is that my lens is probably different to the one that was used in the calibration. And the second one is that the focus position used for the calibration was probably much further away, maybe at infinity, which changed the effective focal length. So for my application, where I take a lot of pictures close up, it's very important to do this calibration myself. So the distortions in real lenses are probably not perfectly radial. And in a moment, we'll do a test to try and evaluate how accurate our distortion correction actually is. But first, I want to talk about two more ways of extracting these points that should lie on a line, because the manual extraction we did earlier is very tedious. The first one is Huggins' program called Calibrate Lens GUI. This program uses edge detection to find lines. So ideally, you just have to load an image into the program and it will find the lines and their corresponding points for you. It didn't work with the photos of my gridded paper, but if you have a different kind of image, then it may work. The other option is what I actually did before. I cheated a little. The coefficients that I showed you earlier are not from the manual process that you saw, but rather from a semi-automated process that I made. And this process only works for the kind of gridded paper. But what happens is that you run a Python script which does the majority of the point extraction for you. If you want to use it, then let me know and I'll put it on GitHub. When you run the script, then it asks you for the image orientation. Then you can select which part of the image should be used, and then it tries to extract all corner points and it puts them onto a grid. And you can manually add points if the script missed them, and you can adjust points if they weren't found correctly. And then it saves all of the data in a format that you can copy into the PTO file that Huggin uses. So rather than using a handful of manually selected points, for this correction I actually used over 30,000 points from over 1700 lines, which were extracted from 20 images. You don't need that many points. It's complete overkill, but it is going to be useful to evaluate how well the correction model works. So let's do that. And what I did is pretty much the same thing as we did earlier with the red lines. So for each of the over 1700 extracted lines, I effectively put a straight line between the two endpoints of the extracted line. And then for each extracted point on the main line, I compute the distance of the point to the straight line. And then I take the maximum over all points of a line. I did that both before and after the correction. And when I sort and plot the distances, it looks like this. The vertical axis shows the maximum distance of the points of an extracted line in pixels. Blue is before the correction and orange is after the correction. The horizontal axis corresponds to the different lines. On the very left end, there are some larger values for both images. But if you look at them more closely, then you'll see that those are lines where my extraction algorithm made small mistakes, where the extracted coordinates are a few pixels off the real coordinates. So let's put those aside. If we look at the rest, then we see that after the correction, the maximum distance of a line is always less than 2 pixels. and it's clearly a lot better than the original image. So this correction really does work very well, at least for my lens. So one last thing that I want to mention is that so far we haven't talked about optical image stabilization. Some cameras, like my X-T4, have a functionality where the sensor moves around to counteract camera shake. And some lenses also have image stabilization. And while that is super convenient for taking pictures without a tripod, it also means that the sensor isn't always in the same place relative to the center of the lens. And even if you turn off image stabilization, to my knowledge, the sensor is usually not locked into position, but it can still move around. We saw that happening on my X-T4 in the video about the do-it-yourself spectroscope. So in general, when we take a photo, then there's a good chance that the sensor is not in the same place as it was when we did the calibration. And that can make our calibration less accurate. I haven't tried to quantify the impact, maybe at some point in the future. In my machine, I'm using my X-T2, which doesn't have image stabilization to avoid that issue. Okay, I think we've covered a lot in this video. If there's anything else that you think I should have mentioned, then let us know in the comments so everybody can benefit from it. If you like the video, then let me know in the comments. Give the video a like, subscribe, tell your friends or anybody else. And yeah, thanks for watching and see you soon.